Imagine walking into a perfectly organized kitchen, every spice labeled, every ingredient sorted by type, temperature, and purpose. Now imagine dumping a bag of mystery groceries straight onto the counter. Ingredients you've never seen, spices in odd proportions, even some doubles of the same item but mirrored. That chaotic dump. That's what early Earth may have looked like after being peppered by meteorites, raw materials scattered across a planetary workbench. But here is the mystery. Out of all that cosmic clutter, something started cooking, and eventually, it cooked up us. This idea that the building blocks of life came from space isn't just poetic speculation, it is grounded in rock-hard evidence. In 1969, a meteorite crashed into the Earth near Murchison, Australia. Locals found the blackened fragments scattered across the ground, and scientists quickly realized this wasn't just any space rock. When they cracked it open, they discovered something shocking. It contained more than 70 types of amino acids, far more than the 20 used by life on Earth. These weren't the kind of contaminants you'd expect from exposure to our biosphere. The isotopic signatures, the distribution, the purity, all pointed to an extraterrestrial origin. And it didn't stop there. Researchers analyzing meteorites like Murchison found sugars, nitrogen compounds, even precursors to nucleotides, the building blocks of RNA and DNA. Molecules that look suspiciously like the tools you'd need to build life, delivered not by a divine courier but by falling stones from space. It's almost cinematic, lifeless Earth, battered by comets and asteroids during the late heavy bombardment, gradually being seeded with organic potential. But here is where things get strange. The amino acids in the Murchison meteorite weren't just random, they were symmetrical. For every left-handed molecule, there was a right-handed twin. In chemistry, this matters. Life on Earth is picky. Our proteins are built exclusively from left-handed amino acids, no exceptions. This phenomenon is called homochirality, and it's one of biology's deep mysteries. If space gave us these molecules, why didn't it choose a side? Even more intriguing, many of the amino acids found in meteorites aren't even used by life on Earth. It's as if nature had a cosmic menu but decided to order à la carte. Life didn't use everything it was given. It chose, it refined, and that suggests that while space might have been the supplier, Earth was still the chef. The kitchen may have been stocked by comets, but it was Earth that figured out the recipe. Now imagine an early Earth, volcanic, hostile, pounded by UV radiation, oceans boiling and cooling in cycles. Into this chaos fell the ingredients of life. Some of them reacted, others decomposed. But in a few quiet pools, under just the right conditions, something began to sift and sort. Perhaps certain surfaces favored one chirality over the other. Perhaps light or temperature biases nudged the balance. Whatever the mechanism, over time, a pattern emerged from the noise. Left-handed amino acids started to dominate. The molecular lottery began favoring structure, and structure favored replication. Replication favored survival, and here we are. This selective refinement is what makes the story so compelling. It's not just about where the molecules came from, it's about what was done with them. Space handed us a chaotic collection of potential. Earth, in its raw unpredictability, sculpted that into something precise, something living, and that should make us pause. Because it means life, as we know it, isn't just a product of ingredients, it's a consequence of conditions. Context matters, process matters. We often imagine origins as singular events, a spark, a moment, a miracle. But this story paints something more gradual, more patient, not a lightning strike, but a slow sifting. Life didn't spring from a single amino acid, but from a system that selected from many. The diversity in meteorites tells us that life could have looked very different. If the balance had tipped toward right-handed molecules, or if a different set of amino acids had proven more stable, evolution might have taken a completely different course. We might not be here to tell the story. This raises an interesting point about life elsewhere. If meteorites deliver this chaotic mix of compounds all across the universe, then planets everywhere could be seeded with organic ingredients. But what gets made from those ingredients would depend on the local rules: temperature, chemistry, radiation, timing. Life might be everywhere, but it might look like nothing we recognize. It might not even be based on the same building blocks. The cosmic pantry stocks the same ingredients, but the chefs, those planets, each have their own methods, their own flavors. And there's something almost poetic about that, the idea that we're not a perfect product, but a successful improvisation. Earth didn't follow a universal recipe. It experimented, failed, adjusted. The amino acids didn't come pre-approved. They were messy, equal-handed, and unfamiliar. But somewhere in that mess, life found order. It chose a pattern, and once it did, it never looked back. So, what do we make of this? It's tempting to see the arrival of meteorites as destiny, as if life was inevitable once the amino acids showed up. But maybe the truth is stranger. Maybe the delivery wasn't a script, it was a gamble, a chance. A roll of molecular dice on a wet, molten rock, and against the odds, order emerged. We started with a question: how did lifeless Earth gain the ingredients for life? And we found a partial answer in the stars. But the real story, the one that matters, is what Earth did with those ingredients, because that's the part that created us. So, next time you hear a meteorite streaking through the sky, don't just think of it as a rock, think of it as a messenger. One that might carry pieces of potential, raw, chaotic, and full of possibility. And remember that what matters isn't just what's delivered, it's what is done with it.